Science matters. Matters can be either a noun or a verb. For the non-scientist, that means everything will be explained, hopefully in clear enough terms that people who have no science background will be able to understand. One of the reasons that it's important to look at science is because of the enormous prestige that science enjoys in our society, common Western culture. That prestige has effect far beyond what I think people appreciate. And it was graphically revealed by a series of experiments initiated by Stanley Milgram of Yale University in the 60s. Although he interpreted it differently and he had a different purpose for it from the moral that I will draw, I think you'll be able to see that the moral that I draw is at least as appropriate as his. The experiment works like this. There are three people who are involved in the experiment. The one who's running it was called the experimenter. And there's someone who's supposed to be learning, and there's a teacher. Now, this is the way it looks. It looks one way, the reality is another way. But this is the way it looks. Two people present themselves as volunteering to participate in this experiment. Psychological experiments on campus are very common, and you pay students. Those days it was $2 an hour, and they did whatever you wanted, sorted shapes or listened to sounds or whatever. And they are told that this is an experiment in learning. And in particular, it's using negative feedback. In other words, someone's supposed to learn something and it'll be tested on it. And when he fails, he'll be punished, to see the effect of punishment on the ability to learn. And here's how it's done. What he's learning is word pairs. The learner is in one room. The teacher's in a different room. They can't see one another, though there's a wall between the two rooms, and as you'll see, it's possible to hear through the walls, but can't see. Now, the teacher speaks into a microphone. The learner has earphones. And the teacher recites a list of word pairs. And then he goes back through the list, one by one, and for each first member of the pair, he then gives 4 options to choose from, and the learner chooses one option. If he gets it right, he goes on to the next entry. If he gets it wrong, the learner is punished by an electric shock. The teacher administers the electric shock. As I say, the teacher has a control which has various settings for voltage and presses a button that administers the shock. It starts at 15 volts, and then each time the learner makes a mistake, the voltage goes up 15 points. If he gets it right, he just goes on to the next pair. Now, before the experiment starts, the teacher is given a shock from the instrument, the 15-volt shock, which is trivial. So he just feels that it's real. When the two volunteers present themselves, the experimenter hands each one a slip of paper, and they are told, on one slip of paper is written the word teacher, and the other slip of paper is written the word learner, and it's presented to them as if the choice of a piece of paper is arbitrary. And then the learner is taken off into another room. Now, the learner makes mistakes, and each mistake he makes, he gets another shock, and the voltage goes up. At a certain point, the learner starts to moan and groan in pain, And at a certain point, he starts to yell and scream in pain. Then he starts banging on the wall to tell him, stop this, stop this. And as you could imagine, the teacher begins to show signs of discomfort, and hesitation. At which point, the experimenter says to the teacher, he encourages him. The first statement of encouragement is, please continue. And if he still shows hesitation, he's told the experiment requires that you continue. And if he still doesn't do it, the third statement is, it is absolutely essential that you continue. And if he still hesitates, he's told, you have another choice, but you must go on. If after all four of those encouragements, the teacher still refuses to go on, the experiment is stopped.
He doesn't.
One second. Now, that's the way it looks. The truth is, there are no electric shocks, and nothing's being taught. And a guy in the other room who's designated the learner is an actor who's trained to act as if he were getting shocks. And yells and screams are recorded, and they're being played back from a recording. And the two slips of paper both have the word teacher written on them. So we guarantee that this schnook over here is the teacher. The other guy, who's the actor, says he got the piece of paper with the word learner on it, but of course it isn't true. The only subject of this experiment is the teacher. How far will he go? How far will he go in administering electric shocks to someone who, for all he can tell, is really suffering from these shocks? The top voltage is 450 volts, which is certainly fatal. And if the teacher will administer 3 450-volt shocks in a row, then the experiment is also stopped. In other words, his contribution is stopped. He started this, the first time he did it with Yale students. He asked random Yale students and his colleagues in the psychology department, what do you think the result of the experiment will be? How many would go to the maximum voltage? Both his colleagues and other Yale students said it would be 1 or 2%. As a matter of fact, 65% were willing to go to the maximum voltage. Of course, they had to be encouraged, and they did show signs of discomfort, and at one point they would ask, maybe we should stop it, and so on and so on. But 65% went to the maximum voltage. And this experiment was repeated in other universities and other places around the world, and the results were consistent. The ones who were prepared to go all the way to fatal voltages were 61 to 66%, regardless of time or place. Furthermore, as another observer of these experiments pointed out, even those, the 30% or so, who refused to go to the fatal shocks, none of them said the experiment itself should be stopped. They didn't protest, they didn't threaten to going to the newspapers to have it shut down. They didn't want to do it, but they didn't threaten to shut it down, nor did any of them initiate going to check on the condition of the learner, supposed learner, was the victim of the shocks, to see if he's okay. So although they stopped short of administering fatal shocks, they didn't threaten the experiment itself. They just didn't want to go that far themselves. Now, I'm looking at some of the other variations that we're thinking of. What was the point of the experiment, and what explanation or what interpretation did Milgram and his colleagues put on it? It was testing obedience to authority. This was right after the Eichmann trials in Jerusalem, and they wanted to see how people respond to authority. Could a person be so influenced by authority to give up his otherwise moral convictions? None of these people, we assume, would randomly inflict pain on other people, and certainly not to the point of fatal shock. But here, in this circumstance, they gave up their own, with misgivings and with worries, yes, but they did it. They carried it out to the end. 65% carried it out to the end. Now, Milgram says he was analyzing response to authority. Response to authority. And one could apply it to the Nazis, and one could apply it to various authority structures. That's what he says. But between you and me, boys and girls, he only tried one source of authority, and that is the scientist. He didn't try the governor of the state. He didn't try the local subway designer. He didn't try a mathematician. He didn't try chess players. He didn't try football players. He only tried scientists. To draw the conclusions concerning the nature of response to authority in general from an experiment that only tested scientific authority, I think is a big jump. I think it's a big jump. I don't know how they would have responded in a democratic country to elected authorities, where a person can be president of the United States for 8 years, and after that he's just your local Tom, Dick, and Harry. Of course, he gets paid $2.5 million for every lecture that he gives, but other than that, he's just another person. You see Bill Clinton on the street, you're not going to bow down to him. You're not going to, and if he offers an opinion, you can tell him to his face that he's wrong. He was president, but he's nobody anymore. I think that this indicates narrowly the enormous prestige that science has in our culture. To the extent that when a scientist pressures a person to do something which otherwise would violate his moral norms, they are prepared to do it. And by the way, the experiment was done with men and with women, and the results were the same. And indeed, in one case, where they tried to vary the experiment and use a dog as the subject rather than a human being, all of those who refused to participate to the end were men. The women participated all the way to the end. So if anybody has any sexist presuppositions as to whether women will or men will, that's an interesting variation on the experiment. I think that this makes an examination of science, its status, its reliability, its place in our general thinking. I think it makes it an extremely important matter to investigate. Now, this is going to be an extended series. I often treat these topics at night, but then I have a time limit. I have to, within an hour and a half, cover a whole chunk of material. I'm taking the liberty of doing it in the afternoon, and we'll go slowly, and I'm happy to discuss the ideas that I present. I'm not in any hurry. Some of the things that I want to discuss with you are these. I want to take a look at the reliability of scientific findings, though as we will see that word is prejudicial. The assertions of science, what science says it has discovered. That word is also prejudicial, as we'll see. To see how reliable they are. Science and scientists. We will talk about the age of the earth, and we'll talk about evolution. We'll talk about the status of science given the Jewish picture of how the world really runs. Since God is creating the world at every moment, the world is running on a foundation utterly different from that which science thinks it's describing and discovering. If so, we should ask what position science has, what relevance it has, what status it has. I will spend some time talking about scientific evidence for the soul, scientific evidence for the soul, as opposed to against the soul, which people I think would be the natural finding. I think there's considerable evidence, scientific, as understood philosophically. And we will talk about that as well. Now, I'm not trained in science. So if I make an assertion about science itself, I will always be quoting a recognized authority on science. But I am trained in philosophy. And I have published research in philosophy, particularly philosophy of mathematics. And I have studied philosophy of science. And when it's a matter of the philosophical implications of the scientific material, then I consider myself competent to report my own judgments, though of course I will be trading on the judgments of other philosophers as well. I will not go out on a limb and take a position that's unique and against what the rest of the philosophical community would say. That's an introduction to where we're going. Yeah.
Is it possible that, in an experiment, the expert is a scientist? So obviously they're going to listen to the expert. If you took a different situation, let's say, a rabbi, where a rabbi, he was the expert, of course somebody would listen to him. Maybe it's not exclusive. Maybe it's not because it's a scientist, just because he's an expert in that field.
Maybe, and maybe there are leprechauns. But I'm asking what the experiment shows. The experiment shows that scientists have this kind of enormous authority. It doesn't show that rabbis have the authority. It seems to me one ought to do another experiment with rabbis to see whether it'll be taken that way or not. That's why I said a democratically elected official who has authority in a democratic country might not have the same kind of response from people whom he tells what to do. I don't know. Maybe these are too cheap. I want to know, what does the evidence show? He wanted it to be an indication of how people respond to authority structures. I'm pointing out that the only authority structure he tested was scientific authority. That's all we really know about. Maybe the other is true, maybe it isn't. Let's leave it at a maybe. Yeah.
Is this like to say the Prime Minister of Congo walking down the streets of New York would have very little authority?
I'm not saying any, I'm just saying we don't know. One shouldn't draw conclusions from this experiment about authority generally. One should draw conclusions about what was tested. What was tested was scientific authority. I'm of the opinion that science has enormous authority and reputability in our culture, far beyond what it deserves. When I was teaching at Johns Hopkins, there was a fellow in the physics department who discovered a particle. Okay, the more energy you have, the more particles you find. So it's, there may be an infinity of them. It's not so terribly, but he was considered to be a top physicist, and so the student newspaper interviewed him for his views on religion. Well, they printed the article, and somebody in the philosophy department cut it out and put it on the bulletin board with the caption, "See how many mistakes you can find in this." I mean, he's trained in physics. He's not trained in religion. So why would anybody be interested in his views on religion? Because if he's a physicist, he's super smart, super rational, and therefore his views are super right, even if they aren't about physics. And when I tell it to you that way, it sounds stupid, as it should. But the editors of the Hopkins student newspaper didn't see it that way. They thought it would be of relevance and importance for people to know what this physicist's views on religion are. It's just nonsense. I think that kind of attitude, which people do have, shows that science has enormous authority, carries authority in the society. This experiment certainly supports that contention, and that's why I think it's important to examine exactly what science can and cannot do.
Would we apply the same thing to rabbis and their views of, let's say, scientific things, specifically in the medieval age?
The same here means an authority telling a person to do something that violates his norms. The question is, will he or not violate his norms? I say the experiment hasn't been conducted, and therefore one shouldn't have any fixed view on this subject. The experiment has only been done with respect to scientific authorities. That we have evidence about, and that we can draw a conclusion about. Other authority we don't know. I have no idea what would have happened in the Middle Ages if this experiment had been carried out with rabbis. Neither does anybody else have an idea.
That isn't what I meant. I meant if, let's say, we have a certain medieval rabbi which was talking about a scientific matter, would we also hold him authoritative? We're not talking about holding a person authoritative. We're talking about the authority telling a person to violate his moral norms. How far will he go in violating his moral norms? We're not talking about whether I believe him or trust him and so forth and so on. We're talking specifically about a person violating his moral norms because the authority told him to do so. And that, I think, we only have evidence with respect to scientists. We don't have evidence with respect to anybody else. Okay, what I want to start with is scientific information. You could divide science broadly into a method and results. Scientific method is a matter of gigantic controversy. There are some philosophers who say there is no method to science. And if you invent a method, you're putting it under constraints that it doesn't deserve. You're going to shackle people and they won't be able to find new theories. There's no method what's at all to science. And others will think that there is a method, and they describe it in various ways. It's a gigantic, difficult subject.
why the method should be successful is a difficult subject. I'm not talking about that. I'm not going to go into that. What I want to talk about is information that science presents as discovered, found, scientific findings, scientifically verified information. And I want to ask, how reliable is that information? How reliable is it? What you get in the normal science textbook. You go to a science museum. Science museum presents you exhibits which acquaint you with how the world goes, what it is, how it's made, what its mechanisms are. I remember when we were living in Baltimore, Science Museum had an exhibit about how the continents got their shapes and their relative positions. Well, they had people from history. Each person was a cartoon figure with a cartoon bubble with his view, obviously making fun of them. And finally, you have the exhibit of plate tectonics. Plate tectonics is the current description of how the continents got their position, their shape. Of course, the idea was, look at all these people in the past with great names who made such foolish remarks about it, and now we know the truth. If I had been designing that experiment, I would have had another panel. I would have dated it 2015, and I would have put a question mark. This is what we're saying today. But what will be in 2015? They don't have those kinds of things. You don't have that in science exhibits in science museums. They show you the truth. Right? May not turn out that way. There's no uncertainty. There's no worry that maybe the foundations might not be correct. It's just a presentation of information. Now, I want to look at this information that science presents, what you get in the New York Times Science Supplement. You know, they report to you that the laboratories found this and the astronomers found that, and see what the reliability of this information is. I think it is of variable reliability. Not all of it is the same. Some of it's more reliable, some of it's less reliable. I would divide this information into 4 categories on a continuum, from most to least reliable. I will describe the 4 categories and show you why the first is more reliable than the second the third the fourth. And then we will draw a moral from this distinction of different levels of reliability. The best case is repeatable, observable phenomena. Things that you can observe with your own senses over and over and over again. And where science says, when you observe X, you can expect to observe Y. These things are either things that happen by themselves spontaneously. The sun comes up, the sun goes down, the stars come out, the seasons change, the plants grow in the spring and they die in the fall if you're in a northern climate. Animals reproduce and grow and develop and die. Human beings are born and grow and die. These are things which you can observe because they happen over and over again. They're repeatable and observable. Or they're things you can make happen. You can hard boil as many eggs as you want. Heat up the water, put a raw egg in and watch it happen. You can break glass as many times as you want. You can bend metal. You can plant different seeds in different environments and check how they grow because you can control it. Repeatable, observable phenomena. And science says, when you have this particular observed feature, then you can expect that particular observed feature because they go together. That's where science is at its strongest. But even there it can make mistakes. Even when it's its strongest, it can make mistakes. Water boils at 100 degrees centigrade. But gosh, you know, I was mountain climbing, and when I tried to hard boil my egg, I made a fire and I put the pot with the water on it, brought the water to a boil, I put it in for 5 minutes and I took it out, and it was soft boiled. It wasn't hard boiled, as I'm used to at home. Answer, not on a mountaintop. On a mountaintop the water doesn't boil at 100 degrees centigrade. It boils at a lower temperature. Oh, okay, so it doesn't really boil at 100 degrees centigrade. It boils at 100 degrees centigrade at sea level. Okay, let's put that in. You know, I tried it again, and this time the egg came out hard-boiled after 3 minutes. That's because you use salt water. Salt water. With impurities, the water won't boil at 100 degrees centigrade, boil at higher temperature. Oh, it has to be pure water. Okay, I'll put that in the rule. Pure water at sea level. You know, I tried it the other day, and it didn't work. Well, tell me about your water. Well, actually, I had the water on a potter's wheel, and it was spinning around. So, no, the water has to be still. It can't be spinning around. It won't work if it's spinning around. Oh, so it's still, pure, at sea level. Now, how many other conditions do we need? We wouldn't have known that it has to be still unless someone had tried it on the potter's wheel and discovered that it doesn't work. How many other conditions are being used that we don't know about? Do we ever have a guarantee that we figured out all the conditions? Here's another experiment. Take a container for water that's the shape of a cylinder, flat bottom, and in the center of the bottom there's a hole with a stopper, a circular hole right in the center. Small circular hole. Fill the container with water, just open on the top, let it sit for a while, a few days, and then remove the stopper from the bottom. So the water will drain out the bottom. And as it's draining, the water will start to rotate in a counterclockwise motion. That is in fact what it will do. Now I tried this. Someone will tell you. I tried it in New York, in London, in Paris, in Munich, and in Moscow, and in Jerusalem, and in Tehran, and in Beijing, and in Tokyo, and the Philippines. I really worked on this. I tried it in a dozen places, separated by thousands of miles. East, west, and it always did the same thing. So I now believe, I have very good reason to think that that's what it does. When you have a cylindrical container and you let the water sit for a while so it's still, it doesn't have any motion of its own, and you have a hole in the center, you take out the stopper, as it drains, it's going to start moving in a counterclockwise motion. And then we try it in Johannesburg. And there it goes clockwise. Gosh, did you think that the equator is a borderline for fundamental forces of nature? That below the equator things are going to be different from above the equator? I wouldn't have guessed that. Just turns out that that's the way it is. You would not have guessed, having tried it in all the initial places, that Johannesburg will be different. Just turns out that it is. I have to recalculate what it is that's doing it and why it happens. Do we ever know that we have all the relevant conditions? How will we know that? We'd have to try testing all possible variations. So even when we're dealing with repeatable, observable phenomena, where we're at our most confident, even there, we can't be sure that we have tried all possibilities. They discovered that a bird that's hatched in the nest and grows up normally the way birds do will build a nest next year, even though they never saw a nest built. And we do not believe that the chirping of the parent birds is, giving them instructions for next year's construction project. But a bird who's hatched in a laboratory and fed and released to the wild will not build a nest. Something about being hatched in a nest causes the gelling of a particular part of the brain, which contains the capacity to build a nest next year. Nobody would have guessed that if we hadn't observed it. We would have assumed that nest building is hardwired into the brain of the bird. That's why it doesn't have to see a nest built in order to be able to do it. And since it's hardwired, it doesn't matter where it develops. But it turns out not to be true. Now, how do we ever know that we have all the conditions? We never know that we have all the conditions. So even with repeatable, observable phenomena, where science is at its strongest, there's still the possibility of mistake. Are we together so far? Okay. The next step is what's called interpolation. Interpolation means this. Let's say I'm testing something. And I've tested a number of times under slightly different conditions to see how it works when I change the conditions. So if I think about the conditions I tested, I know what happens. And I have reason, we'll take for granted, to assume that when I try it again under the same conditions, it'll happen again. What happens when I try a new experiment when I've changed the conditions? What do I know about that? One could be very hard-headed here and say, nothing, you haven't tried it yet, so you don't know anything about it. But let's take a case. Here's what I'm doing. I'm taking a cube of sugar and dissolving it in a glass of water. And I'm charting how long it takes for the sugar cube to dissolve in the water. And I'm trying it at different temperatures of the water. 10 degrees centigrade, 30 degrees centigrade, 50 degrees centigrade, 70 degrees centigrade, 90 degrees centigrade. Now, of course, you know what will happen. The warmer the water, the faster it will dissolve. But I'm talking about exactly how fast it dissolves. So I tried it a bunch of times at 10 degrees, and it takes, in this glass of water, in this size lump, 2 minutes. And I tried it at 30 degrees, and it takes a minute and 2/3. And at 50 degrees, a minute and 1/3. And at 70 degrees, a minute, and 90 degrees, 2/3 of a minute, something like that. The rate of dissolving gets faster and faster as we go up the scale. What will happen if I try it at 20 degrees centigrade? I haven't tried 20 degrees. I tried 10, 30, 50, 70, and 90. I didn't try 20. So as I said, a hard-headed person could say, I don't know, I haven't tried it yet. You know, wait till we try it. But no scientist will do that. What he'll say is this: make a graph. Right? Make a graph. This is the temperature, this is the rate of dissolving. And the dots look like this. They go up because it dissolves faster at each time. 10, 30, 50, 70, 90. Now, draw a line connecting the dots. You know, little kids do that. Connect the dots. Right? Now, ask for 20, for which there's no dot. 20, where does it intersect the line? And that'll tell you how fast it will dissolve at 20. In other words, I'll use 10, 30, 50, 70, and 90 to predict 20 on the grounds that it changes regularly, and therefore when it goes to the 20 point, it'll be right where the line is. That's called interpolation. It's called interpolation because I have the 10 and the 30 on both sides. This is in between. That's what interpolation means. Put something in between other things. Now, some imaginative people have pointed out, you have there 5 dots. There are a lot of different ways to draw a line to connect the 5 dots. Lots and lots of ways. Who says it has to be a straight line? You could draw wavy lines, like a curved line, a sine curve, which will go like this, or a cosine curve, which is the opposite, or any kind of scribble to join them. And of course, if you draw a different line connecting the dots, the prediction for 20 degrees is going to be different. It'll depend upon where 20 degrees hits the line. If it's a sine curve, it'll be very high up. You'll predict it'll be dissolving very fast. If it's a cosine curve, it'll be far down. Another one will have a different shape. How did you pick the straight line to connect the dots? And the answer, of course, will be what you all know, that it's the simplest line connecting the dots. Yes, it is the simplest line connecting the dots. And that's definitely the right answer. It's just that, as of now anyway, there's no agreed upon definition of simplicity. What exactly does simple mean? How should simple be defined? It's a subject that people have thought about and discussed and debated, and there's no satisfactory definition of what simplicity means. Number 2, why should the simpler line be preferred? Why? I have read people who write, it's just aesthetically more pleasing. I like it better. It's more satisfying. Isn't that a really extraordinary thing to say? I'm predicting what's going to happen in the real world. I'm going to drop this cube of sugar into 20 degrees, and before I do so, I'm going to predict this is how long it'll take to dissolve. Why? Because I like that line better. It's more aesthetically pleasing to me. It's more satisfying. I get warm fuzzies when I look at that line, and that's why when I drop the sugar into the water, that's how fast it's going to dissolve. Isn't that a little anthropomorphic to think that the world cares what's aesthetically pleasing to me? So, just to sum up, and then I'll take your questions. Sum up. This is where we stand. The judgments of simplicity are usually agreed upon. Usually agreed upon. And when we test them, the judgments of simplicity usually turn out to be correct. We just don't have any definition of simplicity, and we don't have any explanation of why simplicity should be relevant. But those are merely philosophical concerns. They don't affect the practice, scientific practice in this matter, and therefore I'm going to describe this new category, category number 2, interpolation, as very secure, not as secure as repeatable observable phenomena, because there you actually saw what you're predicting. But it's very secure. It's just slightly less secure than the repeatable observable phenomena. Your question?
If you can test a simple line, then why challenge it? If you take the simple line and just connect the dots, then see where 20 is, and then test that. If it's correct, then obviously the simple line is the best thing to use.
Let's see. You had 5 dots, and we observed that there's actually infinity of different ways of drawing lines to connect the 5 dots. Yeah. Now you say, let's test the simplest line, right? And we tested. But now there's also an infinity of ways of connecting the 6 dots. And every one of those was equally tested by your test of the 6th dot, because every one of them is on your 6th dot. So your test...
I lost that.
Okay. Let's say it in detail. We're thinking of, we have 10, 30, 50, 70, 90, and we're testing 20, right? Yeah. Now we say, before we test, let's make a prediction. What predictions can we make? Straight line, right? Or the wavy curves, which give different answers for 20. You're thinking of lots and lots of different lines which give different answers for 20. I said, okay, here we are. We have the straight line answer for 20 and all these other weird curves, and they give different answers for 20. Let's test it and see what happens. Correct. So we tested it. It turns out that the straight line is the correct one. The straight line is correct against all of the competitors which gave different answers for 20.
So you're saying when you add a 6th one, it changes the whole...
Well, what I'll point out to you is when you add a 6th one, you can repeat the same problem. Okay? Consider all the different ways of joining the 6 lines, the 6 dots, including the 20 dot.
Do it again.
You may do it again, but in the meantime, you have no evidence to predict which one you should pick. You only ruled out the crazy lines which differ at 20. There are lots and lots of crazy lines that don't differ at 20. You didn't test those.
If you test it for the 5th one, and then you test it for the 6th one, you test it for the 7th one, and all 3 of those work, then I guess you can figure that for the 8th one, the 9th one, and the 10th one, that's also going to work.
But you understand, when I draw the crazy line, right? When I draw the crazy line, it fits the 6th, 7th, and 8th also. It fits all of them. So how do I know what it predicts is correct? It fits the straight line and all the other crazy lines that go through all 8. It fits all of them. So the question is, how do you pick which one that fit all 8?
I see.
You repeat the same process. Any finite set of points can be joined in an infinity of ways, an uncountable infinity of ways. So whenever you do it, true, you've ruled out some, that's correct. You've ruled out all the crazy ones that differ at 20. But there's an infinity of crazy ones that agree at 20. And you haven't ruled those out.
You have to count those in also.
Well, in the next stage, you have to count those in, right? Yeah.
If there's a finite amount of dots which can be placed, wouldn't that make it... That wouldn't imply that there's an infinite amount of ways to join the dots, because eventually you could get every single possible dot in the... I need to think of how I'm going to do it.
Yeah, but it's not a question of implying. It's a mathematical fact that there's an infinity of dots. Now, what you could do, theoretically, is do so many experiments that there's and it's impossible to physically discriminate the inputs anymore. That could be done, but it would be a gigantic expense. It's never been done, and we make predictions confidently without doing that. The goal here is to explain how we make our predictions, what they're based on. Right? In that case, you would reduce case 2 to case 1. That's true. But that would be something that no one has ever done.
Don't computer predictions do that?
I'm talking about experiments in the real world now. I'm not talking about computer. That's mathematics. Yeah.
So you're saying that why would you use a straight line? Only for the simplicity of it.
Right.
That's what you're saying. But I mean, if that's true, I mean, why would you throw in any other formula? I mean, like
ever, you mean?
Yeah.
Okay, so
they govern certain different laws that you're trying to figure out, one way or another. Why would you?
Okay, there are times when I get the exact opposite result. I try the straight line, and my observations ruin the straight line. They violate the straight line. For example, if I chart radioactive decay, it's not going to work out with a straight line.
Right,
it's going to be a decreasing curve like that. So, or acceleration. You know, we're talking about accelerating speed, motion. So then it's not going to work out that way. And then I'm going to have to talk about the simplest type of curve that fits the points for this type of phenomenon, where the straight line is, it's not a linear phenomenon, so it's ruled out.
I mean, in the thing you're dealing with, it's pretty clear. It's, two variables, and on a graph, it's.
Oh well.
We're talking about variables. You're going to throw in other stuff only if there are other variables.
Yeah, you're quite right. If you have an algebraic representation of the graph, then you've already decided which curve you want. But we're trying to induce that from the data. Right? That's why I said you could have a linear curve, or a sine or cosine. They are algebraically very different from one another.
You're going to graph it before you put it down on.
To decide an algebraic representation is already to have chosen a particular way of joining the dots. My question is, how do you choose the way of joining the dots?
You just take the contemporary of the time or whatever. I mean, you're talking about how okay, maybe 100 years ago would have been different, but nowadays, assuming that nowadays is possibly correct, and maybe 100 years from now it'll be different. You just choose what we have now and you go with that.
Yeah, I'm not quite sure that that's answering my question. By the way, the number of variables isn't the issue here. In radioactive decay, you only have one variable. You have the number of radioactive atoms as a percentage of the totality of the substance. There's no other variables there, and it still has a nonlinear curve. It's not the number of variables that counts; it's the type of phenomenon that it is. And we know from experiment that the type of phenomena, different types of phenomena, get different types of curves.
And the way it occurs.
And the way it occurs, right? But all that is after I've decided to analyze the data one way rather than another. Right? And the key to all of these decisions ultimately is simplicity. And as I said, I'm not challenging simplicity as the right criterion. It is the right criterion. I'm just pointing out that there are two substantive philosophical questions that don't have answers, but I'm inclined to say it's not so important. Even though I'm a philosopher, I'm inclined to say it's not so important. We do use it. There's very regular agreement as to which is the simpler interpretation. Simpler curve, when it's fitting. Well, maybe I should stop and expand that a little bit. Yeah.
Yeah. As mathematical systems usually run a minimal energy throughput, wouldn't it be reasonable to assume that the most simple line is the one that was created with the least effort, without any waste, for example, of color on the paper or of paper space or whatever, thereby defining simplicity by the line with the least effort, and thereby saying that a straight line is indeed correct?
It's not a question of finding a definition. It's a question of a definition that agrees with our judgments about what to do in real cases. There are thousands of cases where data has been interpreted, and there are any number of different possible interpretations, and we opt for the simplest. What we want is a definition that describes our actual judgments in real scientific cases. Not a question of how much lead did you leave on the paper. That definitely won't work. And that, for that, there's no accepted definition. I should say, this is the virtue of doing it slowly, because I never put this in before, but with simplicity, I'm talking about the simplicity of joining dots on a piece of paper. When you deal with explaining how the world works, it's not so simple. You want to know what makes a typhoon, or what caused the economy to go up and down, and so on and so on. Somebody proposes a theory, some propose another theory, and people say in general you should choose the simplest theory. There it's much worse. What makes a theory more simple than another theory? So you hear people talk about Occam's razor. Occam was a medieval philosopher, and he said, of course we're saying it in translation, it's not clear what he said, but usually reported, don't multiply entities beyond necessity. When you say, you're going to explain how it happens, you say, well, there are atoms, and then there are molecules, and then there are forces between the atoms and molecules, and then there are particles, and well, that's a lot of stuff, Don't put any stuff in unless you really need it. If somebody can get by and explain it with less stuff, it's a better explanation because it's simpler. Yeah, but then some people tell you it's not the number of things you put in, it's a number of assumptions that you make. How many forces are there? Forces aren't things. Forces aren't stuff. Forces are how things react to one another. Now let's say you have one theory with 17 things and 3 forces, and another theory that has 5 things and 9 forces. Which one is the simpler one? Do forces and things count equally? Is one more important than the other? Not a clue. Not a clue. Again, in concrete cases, people are pretty confident, and there's pretty widespread agreement which counts as a simpler theory. But if you ask why, and you try to concoct a definition of what counts as the simpler theory, very, very difficult to come by. It also may reflect your commitments. Stephen Hawking writes that when they discovered the universe is expanding, and the natural thought was, gosh, if it's getting bigger, then in the past it was smaller. That sounds right. And you go further back in the past, it gets smaller and smaller. There's got to be a limit to this, It can't get smaller than 0. So it's got to have a beginning. If it's been getting bigger and bigger, in the past it was smaller and smaller, it's got to have a beginning. Well, as a matter of fact, in the 1930s, they avoided that conclusion. They actually avoided it. They found a way to describe a universe that's expanding, in some sense or other, and never goes back to 0. In fact, let me say it a little more carefully, according to their theory, things are getting further and further away from one another, but the whole is always staying the same size. How do you do that? You say it's infinitely big. It's infinitely big. Space is infinitely big, there are no limits. And it's filled with an infinity of stuff scattered around. Now, it's true. Things are rushing away from one another. That's what the redshift shows. Everything is getting further and further away, but there's plenty of room. You're not going to run out of room because there's infinite room. Our world doesn't seem to be getting thinner and thinner. That's because everywhere new stuff is coming into existence out of nothing, ex nihilo, in order to fill the spaces. That was the steady state theory. The universe is infinitely big, everything's rushing away from everything else, but new stuff is coming in the middle, and don't worry that you don't see it. In a cubic meter of space, in 1,000 years or so, one atom will come into existence. So it's not as if you're going to have new petunias in your backyard overnight. It's the rate of appearance of matter is very, very slow. We'll never be able to observe it. Now, why did they opt for that? Infinitely big world, and new stuff coming into existence out of nowhere, because, as Stephen Hawking writes, we didn't want a beginning. We didn't want a beginning, because a beginning smacks of supernatural intervention. Those are his words. And therefore we opted for a theory that avoids a beginning. Which theory is simpler? Which theory is simpler? An infinite space, which you don't observe, and new stuff coming into existence everywhere in the universe, which you don't observe. Aren't you multiplying things here? You're multiplying new creative episodes all over the universe, which you don't observe, and an infinity of space, which you don't observe. To avoid what? To avoid a beginning. Is the beginning so terribly complicated that it deserves to be avoided by postulating infinite space and new stuff coming into existence all over the universe? I don't know whether that's an obvious judgment of what's more simpler, what's less simple. That sounds like, as he says, we don't want a beginning. We don't want a beginning.
That's just because sorry. That's just because you raise other questions. Like, it's not simply the beginning, it's simply like, where is the beginning? What started it? It's not that, like,
well,
it's because they don't have the answers to that.
If you'll ask the parallel questions about the infinite universe, like, where is the stuff coming from that's coming into existence ex nihilo throughout the universe? I think if you're going to ask about the origin of at the 0 point, you ought to be asking about the origin of all this stuff that just appears from nothing out throughout the universe, right? And you could ask what sustains the existence of the universe as a whole. I mean, it's not obvious that the questions are not parallel on two sides. I'm just pointing out that these are delicate judgments, and I think it's very remarkable that when people make these judgments, they agree. Even though you can't spell out what your criterion is, you can't spell out what your definition is, people do agree. Since they do agree, I say it's reasonable to rely upon it. It's reasonable to rely upon it. That's why I say it's Very reliable, not as reliable as repeatable observable phenomena, but very reliable. And I'm not going to issue any critique of this second category, just to point out that it's got question marks about its basis. Yeah.
Assuming that the whole thing you're saying is true, from like talking about that the universe existed when it started from zero, and then it's continually getting bigger, would that denote the fact that that as it gets farther away, or as it gets bigger, that things come in and out of things come into existence faster on a short period of time?
I mean, according to steady state theory. Steady state theory was canned in 1965 because they discovered the background radiation, which indicated that the universe did have a start from a very small state.
Right, but that doesn't get rid of the whole theory. It's just
sure, well, but you don't need it then. The idea of things coming into existence was only to plug a hole. If you say that space is infinite and things are rushing away from one another, and you stop there, that things ought to be getting thinner and thinner through time. The conglomerations of matter ought to be getting thinner and thinner through time. Right? There ought to be bigger and bigger distances between items through time. We don't see that. We don't observe that. How to account for the fact that space is not thinning out? Answer: new stuff is coming in throughout. We didn't observe that, but we're just using that to plug the hole. How come things aren't thinner and thinner? Once you give up the idea that space is infinite and things have been expanding from forever, so they're running away from forever, right? And you say the universe had a beginning, and a beginning a finite amount of time ago, I don't need to plug the hole with that. Was it a speculation put in just to plug a hole?
Is it that far-fetched to think that things come into existence out of nowhere? I mean, we see that on a daily basis.
You never see that. In fact, according to contemporary science, you have the law of conservation of mass energy. When you start an experiment, to end experiment, you have the exact same quantity of mass energy at the beginning and the end. That never changes.
You're talking about things coming, but there are things that come in and out of existence.
Well, I know what you mean by existence. If a thing came into existence, then in that box there would be a net gain in mass energy.
Right.
But it never happens. But it never happens.
Without something alive.
That's right. Well, here we're talking about a net gain.
Right.
Talking about a net gain. That's never observed. Every experiment that we have performed and every observation we've made, mass energy remains constant. If you will discover a change in mass energy of an experiment, you will win the Nobel Prize for sure. Your name will be written in the history in the science books for at least 100 years, and that's one of the most. And by the way, that wasn't so solid. I mean, 150 years ago, they thought mass never changes, and energy never changes. Both of those turned out to be wrong. It's the sum total of mass energy that doesn't change. That's because of Einstein's relativity. Sorry?
It might be that question mark in science music.
Yeah, it might be the question mark in science music. But today, to create a theory in which new mass energy is coming to existence throughout the universe all the time, when in every experiment and every observation we make there's never any change in mass energy, is a gigantic step. Right? And I did it just to plug a hole to avoid a beginning. Right? Yeah. Okay. We'll pick it up tomorrow in the session.
Isn't that the concept of entropy? How everything stays in the